Hi, everyone. Hello, everyone. Good evening. I'm Melody Hageman, and I will be running the Module 4 webinar this evening for Project Guts. Welcome. Just a real quick review of how to ask questions. You are free to ask them at any time in the chat window. You can also just, if you have a question, turn on your microphone or signal somehow that you have a question. For the beginning portion, I'm going to go ahead and just mute everyone until we open it up for questions. But if you have something pressing, go ahead and put it, like I said, into the chat. And we have Irene Lee, who will be graciously monitoring those questions for us this evening. Okay, so I'll go ahead and mute everyone just in case. Okay, so we're going to start out by making sure that everyone is clear on making your portfolios public and how to add documents, especially Google documents, to your portfolio for Project Guts so that we as facilitators have an easier time and can access those documents and give you feedback and everything. So to start with, I'm going to assume that everyone has created their Google site, which is going to be their digital portfolio for Project Guts. So it probably looks something like this, minus my little pop-up penguins thing. Let me share my screen here. Okay. There we go. All right, so let me show you that again. It should look something like this with your title, and then we had the whole pre-populated menu there for you. And one of the things that you've probably already done is added documents in here. Now, if you are just attaching Word documents or files that you've downloaded and saved to your computer, you can do that simply by going to Add Files, and then you can select the file that you'd like and open it, and that will attach a link to that document. But what many of us have come across is that we have all these tech-savvy teachers using Google Documents, and so using Google Documents. And so if you have a Google document and you want other people to be able to see it, you have to first share that document. And so that's what I'm going to take a moment to show you how to do. So this is just a generic Google document. And in here, once you're done with it and you're ready to share, you need to go to Share and then Get Shareable Link. I already did this for mine, but if you click on Get Shareable Link, that automatically makes it public to anyone who has the link. And that's what we want. We want to be able to see your documents in your portfolio. So please make sure you go through the documents that you've posted in your portfolio and that they are shared this way. So once you have done Get Shareable Link, you don't have to actually email us the link. You could copy and paste this into your portfolio. That's one way to do it. But let me show you how to actually embed something into your portfolio. So let's say teaching Module 1. Everyone had to do Module 1. And if I wanted to add a Google document to this, I wouldn't go to Add Files like I would for something on my computer. I would first go to Edit Page, which is the little pencil icon there. And then I put my cursor wherever I'd like to. So I'm just gonna put it in between these two words to show you how this works. And then you go to Insert, and all the way on the right there are all your Google options. If you're using Google Drive, this is what you'll do. And if it's a document or a presentation, whatever you want to embed on your website, you'll select. I'm going to select Document. And then there's my generic document, testing 1, 2. You can choose the height, so you can make it smaller. I recommend you just choose a height, and then it will automatically choose the width for you, so you don't need to put anything in there. That'll scale it to size. And then you click Save. And when you first do this, you're going to have something kind of silly looking. It's just going to be very blank and generic looking. But when you click Save, it should actually load a real image of that document as it is. So that is how to upload and embed Google Documents into your GUTS portfolio. The other thing to make sure that you have shared it. And so just taking the link, making sure that it's public, anyone on the internet can find and view is good. You could also change it to anyone with the link. We just need access once you've put that in the Google form that asks you to fill out your information in your portfolio at the beginning. So I think we've got most of your portfolios. Just gaining access to the documents that you guys embedded is the most important thing. So, all right, we've got that out of the way. Let's go ahead and dive into Module 4. So this is the physical science or chemistry module. And I'm going to go ahead and pull up all of the documents for this. So in the in electronic form, and this is accessible from our Project GUTS resources page, which is projectguts.org/resources. You can scroll down and all the modules are there right at the top in order. And so the way I got this was going to the PDFs, and then it takes you to code.org and you find the module 4 and you can download those. So this is the complete curriculum for Project GUTS Module 4 Physical Science Unit. So it starts off, and we're just going to kind of go through the pacing guide to give you a general overview. And we've got just our introduction at the top, and then the pacing guide is a couple pages down. And allow me to zoom in a little bit so everyone can see. So the pacing guide is always going to start, much like with Module 1, with an introductory activity, something to engage students. And in all the other modules, we have a participatory simulation where the students are actually actively acting like agents or acting as a system. But for this one, it's a little bit different. So this one has a live demonstration of the silver nitrate and copper chemical reaction. And it could be done with a video. There's a really good video. You have this available to you in the MOOC, or it can be done in real time. So we open up by reviewing properties of matter. This is one of the modules that does require some background knowledge. Some of it's built in, but they definitely need to have an understanding of the things laid out in the module. And then the demonstration is our engaging activity for day 1. Then they get to preview the chemical reaction base model. And then we wrap up discussing signs of a chemical reaction and also what evidence of that we saw in the model. So that's day 1. And let's see. So in the Project GUTS Star Logo Nova galleries for Module 4, we have all kinds of different modules. And so what they would be looking at is the starter model, as it so is clearly labeled. And there's also a link to this in the PowerPoint that's provided for instructors as well. So how you'd walk students through this is just give them a preview. They could go under the hood a little bit, but more or less we're trying to engage them in a discussion between what occurred in the reaction in the real world and what is occurring in the model and how that's different. And that's a discussion of abstraction, what we chose to include and what we choose to leave out. But just a real quick, how to zoom out, what am I thinking there? Real quick demonstration of what students will see on day 1 is you set up and you have these water molecules. So we've got a solution we're going to create. We add a copper strip and then we add silver nitrate. There we go. And when we click forever, they can observe the same sort of chemical reaction as they saw either in the live demonstration or in the YouTube video that was from the MOOC. And so they'll see that there is this silver nitrate floating around, and there's a reaction taking place with the copper, and all of a sudden we have silver. This could be a time to discuss what's missing, but there's also time for that later. So let me go ahead and go through to day 2. And we've got objectives and everything written out there. And then we have day 2. So day 2 generally is about decoding the base model, really getting under the hood and figuring out what's going on, and then making little changes to get a deeper understanding of it. So in day 2, students are going to really analyze the base model. And I'll show you the form that they're going to use to do that in a moment. And then they are going to follow some simple instructions to make some changes to the code. And essentially what they're doing is they are either adding another copper strip or moving the copper strip. So they may or may not have looked at the code on day 1, but day 2 they get a chance to look under there and identify the different portions. So one way that I like to run decoding activities, we'll let this load, is to actually give students a chunk of the code. If I can, I do it on colored paper, or colored ink, but if not, black and white is fine. And I'll just take screenshots of the different sections of code, give them to groups or pairs, and ask them to decode and try to figure out in normal human words what's happening in that block. And so that is something that can happen day 1 or day 2. Day 2, they're going to, as I said, be adding that extra copper strip. So you definitely want them to be able to identify where the copper strip is being created. And obviously it's the when add copper strip pushed block of code there. And what values need to be changed in order for them to either duplicate a copper strip somewhere else in Spaceland or to just move it. And then they're going to fill out the model observation form. So they're going to make some basic observations. And this is what the model observation form looks like. So day 2, it's a really good practice for them to get familiar with the activity. They're talking again about abstraction, which was mentioned in day 1, really breaking down the agents, the environment, and how they're interacting all together, as well as what the process being represented is and the different variables. And then they're also thinking about, okay, each time the code actually runs through, what's happening, what exists in this model that does not exist in the real world reaction or vice versa, and getting to see some patterns. So that pretty much sums up day 2. And by this time, they've already looked at the code. They've done a little bit of coding on their own. And day 3, they're going to actually do some more coding and add another breed, which is very exciting. So, excuse me. They start off with a discussion of when does a chemical reaction stop, hopefully understanding that if there's nothing left to react, and specific to the model, if all of the copper is gone and changed into silver, then the reaction should end. And there should also be discussion of what aren't we seeing here, and hopefully by this point students have identified, okay, in the real world, when the silver was forming, the water was also turning blue. And maybe some of them will even understand that that's the production of copper nitrate. So once you've kind of established that that's missing in the model, because as you can see, if we run this guy and zoom in, and my computer is being painfully slow at the moment, as you can see, when we click forever, the silver nitrate is reacting with the copper and forming silver, but you never get those copper nitrate molecules occurring. And so you just end up with silver, essentially, and water, and that's not accurate because of conservation of matter. So students should understand, or by the end of this model, understand that they end up with one thing may turn into something new, but nothing went away. And so that copper, they have to understand where it's going. And so that's what the lesson for this day is all about. So day 3, they're going to modify the module, and this will take a little bit of time. They're going to be adding that copper nitrate. So let me go back in the gallery and show you what that looks like. We can find it. Complete with copper nitrate and hydration without adding more bleeds. Okay. I like this one. And so you could show them this ahead of time so they can see what it looks like, or they could just start on their own. And let's see if this works. Essentially, we should have some cute little spheres of copper nitrate visible after a while. So let's see if that happens. Oops, okay, I think I picked the wrong one. I apologize. So day 3, and there are several complete models in here. This one definitely has it. So they'll be able to add a breed, and they'll also be running experiments using the experimental design form, which I'll show you here in just a minute. But let's see if we can get a nice demo. Give the public what they want. Okay. Okay, and there we go. So you can see that there's this reaction taking place, and once you have a silver, then you end up with these other spheres eventually floating around and turning the water blue. So that's important for students to understand conservation of mass. And then they'll be running experiments. So they'll change the different quantities of copper or silver nitrate and make observations on that using the experimental design form, which is actually, it's all laid out for you here. So this is just a really detailed description of all of the different activities for teachers to use, and then there's student guides as well. Oops, I missed it. Okay. And I went down one day too far. Okay, so let me find the experimental design form real quick. I apologize. It's in here. There's the model observation form, which we saw. And they'll then be using the experimental design form. And this is really great in a science classroom because students tend to think if they're on the computer that they're not doing science, but they also can see when they use the experimental design form, here it is. It really does help them understand those kind of abstract concepts of variables, independent variable, dependent variable. And so here's the form. And again, what they'll be manipulating is how much copper or how much silver nitrate they begin with. So they're asked to come up with a question. And we usually talk about like, how does blank affect blank? Or what's the maximum value of copper I can have for blah, blah, blah. So the nice thing about identifying variables in a computer model is that the independent variable is generally something you are physically manipulating, either with a slider or the code, and that's easy for students to understand. It's independent. So you are independently going in there on your own as an independent computer scientist and changing that value. So they're either doing it with a slider, silver nitrate, right? Or they are doing that in the code by adding an additional copper strip, or maybe changing the size of the original copper strip to be smaller. So that most students will probably just use the slider, but some of them will be curious what happens with the copper. And thus they're really able to understand, okay, if it's something that I'm changing, then it's my independent variable, and anything that I can observe in the model, whether it's something that I count or I time or that I see in the little score boxes or data boxes, that is the dependent variable. And if you stress that to students as well, they really do get it. Another thing that's really easy with a computer model that really stinks in real life when we're doing science is the range of values. And so students, are asked to say, okay, what's the least amount of copper or the least amount of silver nitrate? What's the greatest amount? And then in between those values, how many trials am I going to run? So again, one of the beautiful things about computer models that we want to stress is that it's easy to run all those trials, and it's cheap, and it's a lot faster. So breaking that down is really a great part of building computational thinking, as well as those scientific method skills. And then, of course, you have the typical hypothesis, data, and interpretation, and so on. So that's the experimental design form. It's basically the scientific method designed to get them thinking about abstraction and the benefit of computer models as well, and some of the details that come along with running experiments on the computer versus in real life. So that's day 3. Pardon me while I make everyone dizzy again. Okay. There we go. Okay, day 4. Generally, day 4 and 5 involve more experimentation and then deeper changes and modification to the model. And that's the case in day 4 for this module, and it's the case for all of them, all the other content area ones as well. So in this case, they're going to create hydrated copper ions that turn the solution blue, and that's a reaction, of course, between the copper ions and water. And they're going to characterize the rate of reaction. So at that point, they'll be able to understand more deeply the blue color that's happening. One thing I didn't point out in the model because it wasn't relevant before, but at the end, ultimately, when the reaction takes place, the copper is not yet blue. It's not immediately visible in the solution until those ions react with the water. And so that's what you're seeing here with the white circles or spheres. And then as they engage with a water molecule, then they turn blue. So day 4 is enabling students to do that, as well as understand that process. And they'll also, again, be using that experimental design form for that. And then day 5 is always the most fun because it allows students to kind of choose different factors. And so in day 5, they'll discuss the rate of reaction and what can speed up or slow down reactions, specifically mixing. So how does movement affect this, as well as step size, which is another form of movement. And then they're going to do this, and they will actually at this point fill out the project design form prior to making their changes, which is really great practice in actually planning out a model or a project. And then they'll fill out the experimental design form again and share their findings with everyone. And it's neat because everyone can kind of choose a different design to their project, and they can learn from each other. So hang on just a second. Hey. I have dogs. Okay, so let me show you the project design form, which is way down here. Okay, here's the project design form, and this again is for day 5. In all of the modules, generally, it's going to be the last 1 or 2 days, because that's when students are really comfortable with the code and ready to make their own changes and go on their own and explore. So it's similar to the experimental design form in that they're going to seek to answer a question, but they're also thinking in terms of a real world phenomena or things that they've seen with their model already. And they're also planning out and thinking about what specifically they're going to model and how they're going to model it. So more so than in the experimental design form, where they're just asked to identify what already exists in the model, here they're planning out what agents do I have and what agents am I going to add, and really thinking about what the process in the main for loop or forever loop is going to be, as well as what are some things that we really need to include in here and leave out. So that's our project design form. One form that we don't actually have in this model is the model design form, because at no point are they specifically taking and modeling their own, an entire model on their own. But they could take that forward with this. So those are the lessons for this module. Quick run through. I apologize for talking so much. And as I said, this is kind of the ultimate, the end project, where they will end up with a model that is as accurate as a middle school student can probably understand of this single replacement chemical reaction. And that has a lot of different components that they have added. So there is a run through of our pacing guide, and here is again, in the GUTS library in Star Logo Nova, you have all of these different public galleries that you can use with starter models, and they also have completed models for your benefit as a facilitator or a teacher, so that you have a complete project that you can look off of and see, you know, specifically how certain things were done. So in module 4, we have everything from chemical reactions model with camera on the side, which allows you to see the reaction less from above and more from an agent's perspective, so to speak. And that is really useful, particularly for schools that have Chromebooks and cannot alter the screen or the view without having the agent do that. So that is something that we can look through if anyone's interested. And then, like I said, everything from starter model to we've got the ions to we have the whole hydration process and a line graph, as well as just the basics. So you can see step by step an example of the code that your students will be doing. And it's there as well for your benefit while you're building them if you get stuck. So the base model, as I spoke of, is the starter model. And Day 1, you guys are asked to add that copper strip just like the students. Okay. I apologize. I'm getting lost here. There we go. So starter model is all the way to the right. And let's go ahead and look over that code for the different modifications that you'll be asked to make. And then we'll talk about real quick, just some tips and tricks. And if you have any questions so far about what you have seen in the model, and let me dive to chat real quick. Okay. What you've seen in working in the model, or what you're nervous about, or what you've already learned, we can get into that as well. Okay, so let me view code. Day 1, the task is, well, actually, day 2, I apologize. Day 2, the first day that students actually get into the code, and your lesson 2 is to add a copper strip or move a copper strip. So here is our code where we're setting up water and we're adding silver nitrate and then adding copper strip. So essentially what we have is a few different agents that are red, size 1, and then you'll notice they have different X values. So this first one is X at -1, starts at 25. The second one is X at 1, starts at Y is 25. And the third one is X at 1. Interesting. Oh, sorry, X at 0. Okay, I apologize. And so they're basically, there are agents, 3 of them in a line right about here. And what they're doing is they're going and they are moving forward and creating another agent 49 times. So you're ending up with 3 rows of 50 copper little agents. So what students need to do, or you do, is figure out how you would change the X value or the Y value to end up with multiple copper strips or copper strips in a different location. What's most beneficial is multiple copper strips, because then you could, say, have a button where you add an extra one. So it could be add copper strip, add second copper strip, and that makes easy experimentation later on. So how would we do that? Well, giving everyone time to think. It lies in the location, and so you would need to create copper atoms in a different location and then have them kind of follow the same process. So one common thing that students will do is they'll want to change the X and the Y, and they can end up with some pretty wonky copper strips if they do that. Really, the Y value should be the same, and the X value should be what's changing, so that they're on the same level going downward, all in a straight line. You could, for students that are interested, have them do kind of strange shapes and see if that affects the rate of reaction. That actually should, given that surface area is one of those factors in rate of reaction. But I find that can be overwhelming for students, and so the main concern here is just to make sure that they understand how to place a new copper strip, and that really you're going to be changing the X value. Let me just demonstrate that real quick. So if I did this at, like, actually let's do 10, X is 10, 11, and 12, you'd see that we end up with a copper strip in a very different location. I may not have remixed this. So let's see. Okay. There it is. Okay, so it's moved over. And now that you've seen that, that should be a fairly easy change to make. And also coach your students through. So this is the base model. I think at this time, I'd like to go ahead and open it up for questions. So I'm going to go ahead and stop sharing my screen for the time being. And then if you have any questions, I'm going to go ahead and unmute everyone as well, so that if you have a question, you can just unmute yourself. And if you don't have anything to ask, you can go ahead and just keep yourself mute. So feel free to speak up. It can be about anything this week or last week, specific to the model or teaching the lessons, and I'm here to help.
Melody, there's a chat from Lee.
Okay.
She says, I'm on day 3, but I'm thinking about the day 4 activities. It seems like the higher the concentration of water molecules, the faster the white copper nitrate molecules would become hydrated and turn blue. What would best reflect the real life reaction?
That's a good question. Obviously, this is a reaction that couldn't take place without the water present. And so it's not like we could just really eliminate the water in the real world and see what the effect is. Likewise, in the model, adding more water definitely would have that effect. If you added more water in the real world, I think this is what you're getting at, it wouldn't really make a whole lot of visible difference, because you've got the copper strip, you've got the copper strip, and you've got the water, and you've got the silver nitrate inside the water. And unless you were dealing with a really, really, really high concentration of silver nitrate, which would be really expensive, you probably couldn't see the difference in the real world. So I guess this is something that you could discuss as on a theoretical level, and then talk about the benefits of using the model to kind of illustrate that concept versus the real world, where those are subtle changes that we wouldn't really see when we run the reaction with more or less water, depending, like I said, on what your concentration of silver nitrate and your amount of copper could be. So I hope that helps. Feel free to ask a follow-up question.
Okay, so in real life,
Yes.
The copper nitrate hydrates pretty immediately, right?
Yes.
Okay. So you wouldn't want to lower the water concentration or the number of water agents down to the point where you have a lot of white copper nitrate just floating around, because that's not real.
Right. Yeah, absolutely. And so that may be a direction that you would want to steer students away from when they're engaging in the different variables that they can change, for that very reason, because that reaction wouldn't take place and you wouldn't even see the non-hydrated copper with no water there to make it happen in the first place. Yeah, so that definitely is a concern. Did you want to add anything, Irene?
So that leads me to the question of, why do we have an intermediate coding step to code them to turn white, then to turn blue, if in real life they don't turn white before they turn blue?
This is Irene. I just wanted to point out that there is a good video of the live process, or there are a couple of them linked into our module. I hope you can see them in the MOOC. But the process of turning from, just clear water to blue water happens over the course of, I want to say, a minute, 2 minutes. Melody, do you remember?
Yeah, the initial video is sped up. It's about 30 seconds, I think. He said you're talking about the pipe video that you guys have in the MOOC, right? And I'm going to pull that up and show just what that looks like. But yeah, that's about 30 seconds. So it is something that does have to happen because the water molecules are all there already. It's also something that just kind of happens almost immediately once the reaction with the silver is complete. A lot of people were concerned if we didn't include that it would be misleading. And so that's just a step that happens, that does occur in the reaction, no matter how quickly it is, that we felt was important to include in the model. But let me find that video. Does that help at all, Lee? So I think ultimately, okay.
It does. It helps me explain why earlier on day 1 and 2, we could remove the water agents or not because they don't help or hurt anything going on. We just know they're there. Mm-hmm. Whereas once we start looking at the copper nitrate that's there, the rehydration, or I guess we call it the hydration of that to turn blue, the water does need to be there as an active agent and not just something pretty to remind us that it's an aqueous solution.
Right. I like the way you put that. And I think that's definitely true. I think it all comes back to that discussion of abstraction and what's necessary for us to learn at this point versus later on in as we're more familiar with the module. And so if you're always bringing it back to that reaction, and that's why that video is so helpful because you can show it every day, then students will understand more and more what's going on there, and also what's missing and what's important that's missing, because that's part of the biggest thing with computational thinking is identifying how far we need to take our model before we're satisfied with how accurate it is.
I hope she's okay. I think we lost Denise.
Feeling okay? Does anyone else have any questions? Have you guys dived into the model? Lee, you said you're on day 3. What about, well, we'll let Denise kind of feel better. Did you have any other questions, Lee?
Just curious, I haven't gotten to day 5 yet, but as far as models where they create their own, where have students been so far that you're aware of? Are we looking at other single displacement reactions with different elements, or what do you see them doing?
They could. That's definitely an appropriate direction to take that. The actual task for day 5 is more along the lines of they're not creating a model from scratch so much as analyzing different factors that will affect rate of reaction, specifically in mixing and step size. So let me go ahead and pull up kind of a suggested activity.
Mm-hmm. And the step size is supposed to mimic heat being added to the system.
Yes.
Yeah.
I didn't quite catch that. What being added to the system?
Heat or temperature.
Yeah, raising the temperature.
Okay. Yes. Here we go. So I'm going to go ahead and share my screen again so I can point out just some points of interest in day 5. So again, they're not so much doing a model from scratch, which is why they don't really do the entire model design form, versus the product design form is them kind of picking out specific things from the model and adding those. So, okay, everyone should see my screen. I should stop making people dizzy. So task 1 is discussing what causes the reaction to stop and limiting reactants specifically. And then activity 2 is where they actually plan out and choose one of or both of the kind of tasks with the mixing or the step size. And so if we go through there, mixing is more the simulation of movement with the discussion of wiggle walk versus random walk. They could, as it says here, decide that they want their agents to walk in or move in straight lines, or circles would kind of simulate stirring. And that's when once they've decided what they want to do, then they fill out the project design form. So there's that. And then, as Irene pointed out, the step size is a simulation of adding heat, assuming that they would move more quickly, which would be more steps at one time if it were warmer. So that would simulate the heat. And I do want to point out here, just in advance, I know no one's here yet, but it really is important to not go further than 3 steps. If you have your students, or your agents go 5 steps, 4 steps, 6, 10, whatever. Remember that the width of the copper strip is 3 agents. So they could be going like over the strip, but skipping it entirely, which is not accurate. They would actually, in real life, be bumping into that versus like kind of skipping or floating past it. But those are the 2 kind of areas of focus where they make changes. And like I said, you could do both, or you could have them just pick one and kind of share their findings after. And then once they've made the changes, they run experiments.
That step size, the step size thing you mentioned there, I ran into something similar to that in module 1 when we were playing with the rabbit each other or whatever it was. I had done a detection to where if they get within so many steps, they take larger steps. And what I found is it looked like they were chasing each other around, but they were jumping back and forth. And the visual was that they were banging into each other over and over and over and over and over again, but they were really skipping past each other and not really changing color or infecting each other, I guess is what it was.
Yes, that's a good point. So that's the same situation. Whenever you increase the number of steps, as you said, if an agent is within that range, they do just kind of transport to that number of steps, and whatever pixel or area is that many number of steps over.
Yay, Denise is back.
How are you feeling, Denise?
I'm fine, thank you. Something tickled my throat, so.
No problem. Denise, how are you doing this week with the module?
Well, can you hear me okay?
Yes.
You can, okay. Because I started the course a little late, so I'm a little behind, but I've been just sort of starting the module, the second module. So, but I did have some questions about the agents, like when I was doing the epidemic model, there was just something in the setup of the program I wasn't clear on. Because how can you, I figured adding the random block sort of determines whether a Calliope is going to turn red or black. Well, I was using red and black in my model, but the question is, what determines like what's the collider and the collidee? For example, my feeling would be if two blacks collide, they're okay. If a black and a red collide, it turns red. So it's how can you sort of set it up for collidees to check each other? That's what I thought the program would enable us to do, so that when two agents collide, they can check each other.
That is actually what's happening unless you have some sort of conditional that keeps it from doing so. So basically, every turtle is going to follow all of the instructions inside the turtle tab. And so, and they're doing this every iteration. That is every time they go through the forever loop code. So if I'm a turtle, I'm following those instructions. And so I would say, well, my set of instructions would be if if I collide with someone, then if their color is red, I set my color red or something like that. Meanwhile, the other turtle that collided with me is also checking and following those instructions. So the collidee is the opposite turtle of whichever one is currently following the instructions. Let me see if I can pull up an example and we can talk through the code and maybe I can see what part is more confusing. So epidemic. Okay. Share screen. And view code. Okay, so in our starter model, as it loads, we have blue and red turtles in this model.
Okay.
Oops. Okay, I should have opened my own model. So essentially, you're going to have something along the lines of you have red and blue turtles, and there's a block. Can you see my screen okay? Okay.
Yes.
So there, and then you have something like this in the turtle tab where it's like on collision with turtle. So in the beginning of that, it's just if I run into someone, I change color. But ultimately, it's going to be more like if the color of collidee, that means the other turtle, the turtle I ran into, is red. So if I ran into a sick turtle, then I turn sick, is essentially what's happening here. So if you kind of read it in the first person, like, okay, I ran into another turtle. If the color of the turtle I ran into is red, then I turn red. That's what the turtles, that's how the turtles are reading it.
Okay.
Okay. Did you have any other questions?
No, I think I'm okay. I'm just going to review it tonight.
Okay.
I mean, I've been doing it. I've been putting my links in, but I just think I'm going to review that one tonight to make sure I'm okay with it.
Okay.
Yeah.
Perfect. And if you have any questions, again, feel free to ask them in the forum or in email, and then we'll be having another webinar on Module 4 Sunday. So we'll kind of go over the same stuff, but they're also going to, on the same line, be going over Module 2 and Module 3.
Okay.
Right now, consecutively. So if you want to tune in for those, and there's Sue who's running the next one, you can go ahead and do that, and maybe some more of your questions will get answered.
Okay, thank you.
You're very welcome.
Hey, Melody.
Hi, Sue.
Thank you, Melody.
You are
I
welcome.
have
I'm
a
going to go
question.
ahead and sign off now. But
Great.
as I said, everyone who's interested, the next module is going to have its webinar right about now, and that'll be with Sue, correct?
It will be. I have a question for you though.
Okay.
Are you signed in under the SFI login?
As Project Guts?
Yes.
Yes.
Okay. I think I probably have to go back and sign in under Project Guts
Yes.
because I don't see a record button.
Okay.
Right. I think, I wonder if we can all sign off and sign back in so I can turn the recording off and then start a new recording. I hope it'll do that correctly.
Okay.
Okay. And let's,
I'll go ahead and sign out and
so
Can
did
the
you
original
just,
host pass those privileges over?
All of us?
Hold on. Yeah, I'm not seeing a way to pass privileges over to Sue.
Irene, are you going to be on for this one as well?
Yes, so I could stay on.
Okay. Yes. Because as long as someone's logged in as Project Guts, they can record it, and I see that you are, and you have been.
Yep.
So that
Okay.
should work. Okay, I will
Super.
log out though. Hopefully that'll simplify things. And you all have a good night.
Thank you.
Thanks.
Bye,
Bye.
thank
Thanks,
you.
Melody.
Bye.
So Sue, we can stay on. Let's just keep the line open.
okay.
I'm going to
Okay,
turn the
that's
recording
fine.
off and then turn it back on.
Okay.